Assalamu alaikum everyone. Welcome to this lecture on refrigeration systems. So for the past few classes, we have been talking about refrigeration systems, and we started by talking about the Carnot refrigeration cycle and then the ideal vapor compression refrigeration cycle. So in the last class, we spoke about ideal compression vapor compression cycle and also discussed the actual vapor compression cycle at the end of the class. Today, we will go ahead and use this cycle to solve an example and then talk a little bit more about refrigerants and other innovations that are possible. So let's look at this problem. So this is a simple problem on actual vapor compression cycle. And here we have been provided with the properties at different states, right? And we have been asked to calculate the compressor power, refrigeration capacity, COP, and isentropic compressor efficiency. Now, this is a very simple problem. And most of the problems that we deal with in vapor compression systems are rather easy to work with, having solved much more complicated problems when we were dealing with Rankine cycles and its modifications in chapter 8, or even the Brayton cycle and its modifications in chapter 9. All right, so here we have been told that the table provides all the properties that we need for the vapor compression refrigeration cycle, and it is using R134A as the refrigerant. We'll talk about this more in a bit when we discuss refrigerants. The mass flow rate that is used is 0.08 kilogram per second. So as you can see, it's a pretty small mass flow rate that is used. Okay, so the first thing is to calculate the compressor power. Okay, so this is really straightforward. We have been provided both H1 and H2. So compressor power is simply m dot H2 minus H1, right? Mass flow rate times H2 minus H1. So we have the values already in there. It's just a matter of substituting the numbers in here. And when we do so, we get a value of 3.1 kilowatt. So it's a reasonable amount of power, okay? Not very high, not very low. Now let's calculate the refrigeration capacity. Now this, as I mentioned earlier, is one of the most important parameters when we are thinking about purchasing a refrigeration system or an air conditioning system for that matter. So this is a characteristic of the refrigerator or the air conditioner that you have, and basically defines its performance. So it's equivalent to Qn, right? The amount of heat that is absorbed in the evaporator. So it's equal to m dot times H1 minus H4. We already have these values here. And if the question had asked us to calculate the refrigeration capacity in kilowatt, we would just end here, okay? Just H1 minus H4 multiplied by the mass flow rate. But here we have been asked to provide the refrigeration capacity in tons. So what we need to do is we need to multiply by 60 seconds to convert the kilojoule per second to kilojoule per minute. And then we divide by the 211 kilojoule per minute to convert it into tons of refrigeration, okay? So this basically ensures that the final answer that we get is in tons. So it's basically 3.41 tons of refrigeration, which is a reasonable amount of cooling capacity. Now the COP. The COP, as we have discussed before, is simply the desired output, which is the cooling here, right? H1 minus H4, divided by the required input, which is the work input that we need to provide here. So it's H2 minus H1. So it's H1 minus H4, the refrigeration capacity, divided by H2 minus H1, the work input. Again, we have all the values, just a matter of substituting it in there, and we get this value of 3.86, which is reasonably good COP for a refrigeration system. As you notice, this value is greater than 1, right? The beta is always greater than 1. Okay, now let's talk about the last part, the isentropic compressor efficiency. Now we have been provided the value of 2 and 2s, so it's rather easy to determine that. From the definition of isentropic efficiency, we know that it's equal to the isentropic work input divided by the actual work input. So H2s minus H1 divided by H2 minus H1. This is again a matter of just plugging in the values, and we get an efficiency of 80%, which is again reasonable, but for other compressors, for example, the kind of compressors we were using in the Brayton cycle, we were achieving higher efficiencies. It simply has to do with the kind of fluid that you're trying to compress and a lot of other things, right? So this is not bad. This is reasonably good. But certainly if you can bring this down a little, bring this up a little bit further, right? Make it 85 or 90%. That will go a long way in reducing the work input that's required to achieve the same refrigeration effect and basically increase the COP, which is what we always want, right? We want to spend the minimum amount of electricity to produce the required cooling effect. Okay, now let's talk about the Exergy analysis, right? This is one of the most important things that we would like to do as an engineer. We always want to optimize things. Now, we have discussed the Carnot cycle, and we came up with the definition for the maximum COP of a refrigeration cycle, right? Which is basically equal to the COP for a Carnot cycle operating between two temperatures limits TC and TH. And this is how it is calculated. Now, we already discussed in the last class that although this is how you calculate the COP for a Carnot cycle, the COP for an actual cycle would also vary in the same manner like a Carnot cycle would vary if you play around with TC and TH. That is, if you bring TC and TH closer to each other, right? So if you increase TC or reduce TH, this is going to increase the COP of the Carnot cycle, but it is also going to increase the COP of the actual cycle. So this is a very simple tool if you want to think about it. It's a really simple tool that allows you to imagine what changes in TC and TH will change the COP of actual cycle as well. Of course, the changes that you get in a Carnot cycle and an actual cycle are different, but it happens in the same direction, right? So increase in TC will increase the beta for both Carnot and actual cycles, and reduction of TH will again increase beta for both Carnot and actual cycles. Now, as I mentioned before, the goal of Exergy analysis or second law analysis is basically to identify the regions or the components where the maximum Exergy destruction is happening and try and reduce them in an economic manner, right? So economics is really important. We don't want to come up with a solution which is extremely costly, right? It really does not make sense and it's not practical. So the idea of doing Exergy analysis for any component or any device, it's simply to identify first of all, right, where the destruction is happening. And then based on that, we can make a decision on how we can reduce that destruction. Now, the way to calculate Exergy destruction is through Exergy balance, and you're all very well aware of this, having covered that in chapter 7, and even having studied for the midterm recently. So when we talk about refrigeration systems, we usually deal with a single inlet, single outlet control volume, which is at a steady state. So the Exergy balance reduces to this more specific form. And for all the refrigeration cycles that we talk about, the changes in kinetic and potential energy are negligible. So the specific flow Exergy change, which is EF1 minus EF2 for any given two states, is simply equal to the changes in enthalpy minus T0 times the changes in the entropy. All right, now let's go ahead and solve a problem based on this. Now here we need to calculate the Exergy destruction in the compressor and the expansion valve of a refrigeration cycle. And what the process that we use here is very similar to what we have done earlier in chapter 7. The only thing new here is the fact that we are doing it for a different fluid, right? We have never used R134A. We have used water, or we have dealt with air as a working fluid. So you just have to go to the appropriate tables, right? There's no other surprise in here. So for this specific question, we have been again provided with the properties, right, at all the states, 1, 2, S2, 3, 4, and also the entropies at 1, 2, 3, and 4. So let's start with calculating the Exergy destruction for the compressor. Now, the general formula for Exergy destruction is given in this manner. So the Exergy destruction is equal to the Exergy transfer associated with heat transfer minus the work output plus m dot times the change in the specific flow Exergy, right? So EF1 minus EF2. So this is what we need for the Exergy destruction rate for the compressor, right? Because it's going from the state 1 to state 2. Now in a compressor, we don't have any sort of heat loss happening. And actually there's no work output being produced. We actually have to provide work in. So as we know, work out is actually equal to minus W dot N. So when we write it in this form, when you write it in terms of the work input, this is how it's going to look like. So it's just work input plus the change in the Exergy. Now, for this specific case, because there's no heat loss happening within the compressor, from energy balance, we can easily find out that W dot N, or the work input required, is equal to M dot H1 minus S2. So these two get canceled here. What we are left with is simply the product of change in entropy times M dot. So if we substitute the values given in the question, right, and the table, for S2, S1, T naught, and M dot, we get a value of 0.58 kilowatt for the exergy destruction of the compressor. So I mean, here we have not calculated the exergy destruction for an expansion valve, but in general, you should know that the largest exergy destruction occurs in the compressor when we talk about the vapor compression cycle. If it's happening in any other component, then that's something that you can figure out and reduce in an economic manner. So when you have calculated already this value, you already know that the exergy destruction for the expansion valve should be lower. If it comes out to be higher, you know there's a calculation mistake. Okay, so when you're doing this calculation, you should always have some idea about what to expect, right? I mean, of course, you can expect what this value would be, but you can expect which one would be larger. Okay, and if it's not, then that's a hint for you. All right, now let's look at the exergy destruction for the valve. Now for the expansion valve, again, this is the general form of the exergy balance equation when we're trying to calculate the exergy destruction. Well, in an expansion valve, there's no work output, there's no heat transfer, okay? The specific thing about exergy, the specific thing about this expansion valve is the fact that it's an isenthalpic device. So the enthalpy remains same, right? So H3 is equal to H4. All right. So when we calculate the exergy destruction, the first part cancels out. Okay, we are just left with the change in the entropy. And when we plug in the values, it comes out to be 0.39. So this is as per our expectation, right? It should be lower than what we have here. Now, in terms of exergy destruction, I mean, there's not much we can play around with this, right? If let's say we had another way of dealing with going from state 3 to state 4, maybe any sort of other expansion valve where the entropy reduction is smaller, we can think about it. But as of now, it's not bad. If this value was, let's say, 0.7 or 0.8, which was greater than the exergy destruction for the compressor, then we would think about redesigning the valve. But for now, it's reasonable. All right. Now let's talk about how do we select refrigerants, right? The refrigerant is basically the working fluid in the refrigeration cycles. In the examples that we just solved, we were talking about R134 as R134A as the refrigerant, which is one of the most common refrigerants. But let's see what is the general criteria and how did we actually come up with selecting R134A. All right, so when you're selecting a refrigerant, this is basically done on a lot of factors, right? It's not just one. There are a series of factors that you need to take into consideration, with each factor having its own priority and its own weightage. The first and the most important factor is the performance, right? We need to have a refrigerant which provides the adequate cooling capacity that we need in a very cost-effective manner, okay? So these two are really important. So what does it mean when we say we want adequate cooling capacity in a cost-effective manner? First of all, it needs to be something that's very cheap and it's easily available in the market, right? You don't want to have a you don't have a designer refrigerant which is costly to obtain and it's not even there. The other very important thing is the pressure-temperature relationship that exists for the refrigerant, right? So it's a function of its properties. So we know that the saturation temperature at the condenser pressure, P2, should be higher than the TH or the temperature in the ambient temperature, right? The temperature of the room. So Tsat at P2 should be, 45 or even higher, right? This is a necessity. Otherwise, the cycle cannot work. It cannot reject heat to the environment. The other requirement that we need for the vapor compression cycle is the fact that the saturation temperature at P1, which is the evaporator pressure, should be lower than TC, right? Whatever your desired TC is. In the freezer, it's minus 18 degrees Celsius. In the fridge, it could be 3 degrees Celsius, right? Or it could vary depending on what's the need. So having that fixed, we need to ensure that the P1 that we have, right? That is the evaporator pressure, should be greater than the atmospheric pressure for the refrigerant we are selecting. Why do we need that? Well, if it's not the case, then air could leak into the refrigerant and that will just spoil the system. You never want that, okay? So this is one important criteria. The other thing is we want to try and ensure that P2 is not very high, right? So we said the saturation temperature at P2 should be greater than TH. Well, we can always play around and keep pumping it to higher and higher pressures until we reach that, right? But we want to have a refrigerant whose P2 is as small as possible, right? So if P2 and if the difference between P1 and P2 is small, if P1 and P2 are closer together, then the compressor work input is smaller, which is what we always want. The third thing is the heat of vaporization, which is basically the heat needed to convert it from liquid to vapor state, right? So HFG. This needs to be as large as possible. And the simple reason why we want this to be large is because for larger HFG, we can achieve the same cooling capacity with small mass flow rate. And small mass flow rate means small compressor and small evaporator, small condenser. Everything becomes really small, which basically comes down to cost savings, right? So essentially, it's just a matter of good cooling capacity in as cost-effective manner as possible with as high COP as possible, okay? So this is the whole game here that's really important. Once you have taken care of the performance, you need to also ensure that it's safe, right? We should not select something that's toxic or flammable, okay? Although this is not always an option, but we should try whenever possible. The third thing is to ensure that it's really chemically stable and it does not react with the tubing and break it down. And it should also not be corrosive, right? So corrosion basically is something that eats away the metal and converts it into some other oxides. And that again is something you don't want because it'll break the tubing and it'll just cause a refrigerant leak, which is the worst thing possible, right? You do never want that. The last but not the least factor that also is really important is its environmental impact, right? We want to ensure that we are using a refrigerant which does not damage the ozone layer, right? We want the ozone layer to do its job and block the UV radiation and keep us safe. And we also want to have a refrigerant which has minimum impact in terms of global climate change. So we already are aware and are seeing the effects of global climate change with increased temperatures or extreme climates happening in the last few years and last few decades. So we want to ensure that we are taking care of that as much as possible. So when we look at all the above criteria that we have discussed, there are a lot of refrigerants that fit a lot of these criteria, right? Some are better, some are worse when we look at the above criteria. So a lot of refrigerants such as chlorofluorocarbons, ammonia, hydrocarbons such as propane, ethane, ethylene, so on, even carbon dioxide and air, for example, in the aircraft, and even water has been used, right? So certainly water is something that you can use when your applications is above the freezing point, right? Below the freezing point, you can't really use it. So a lot of refrigerants have been tried around, okay? So a lot of different refrigerants have been used for different applications. But if you look at the market, the 90% of the market is basically captured by R11, R12, which are the chlorofluorocarbons, R22, which is hydrochlorofluorocarbon, and these CFCs, chlorofluorocarbons, these damage the ozone layer, right? So they were initially used, but then they were discarded later on. They're still being used in some countries though. And R134A, which is a very common refrigerant, and R502. So these are the ones which are capturing a lot of the market. When we talk about the industrial and heavy commercial sectors, they tend to use ammonia because they can maintain, they can have the maintenance and the safety protocols followed very strictly, which you cannot always do, especially the maintenance protocols cannot be done at home. So they can use ammonia for getting better COPs. We really can't do that. And that's why these above refrigerants, which I mentioned, are the ones that are used, that have captured the majority of the market. Now, R134A has been used to replace R12 in a majority of countries, right? And R134A is used in fridges and freezers, as well as in the air conditioner that you find in your car. So, if you Google the model for your refrigerator, you'll be able to see what refrigerant it's using. More often than not, it's R134A that's being used, right? So do check that out. When we talk about window air conditioners, we use a different kind of refrigerant. It's R22, which is a chlorofluorocarbon, right? It's not as bad as the CFCs. It does not damage the ozone layer, but it has its own issues. But again, it is really beneficial in terms of performance. So it is used in all window air conditioners, even now, right? Even what's sold in the market. And it's used in heat pumps and basically large industrial refrigeration systems as well. So it's another very favorable refrigerant. So in the project that you will be assigned maybe sometime later this week, you will also be comparing several refrigerants for a given refrigeration system, and also will be solving a problem on the Brayton cycle, basically the gas turbines, because these two things are really important for Saudi Arabia, right? As we mentioned before, 50% of the energy needs are being met by gas power cycles. So you need to know how to solve that. And refrigeration is something really important for a hot country like Saudi Arabia. All right, so now let's just look at the listing of different refrigerants which have been used throughout history. And there are a couple of things that you want to ensure. First thing is you want to ensure that the global warming potential is as small as possible. Okay, for CO2 is 1, and you would want to keep it as low as possible, right? Because it just causes global warming. The other thing is we want to try and avoid CFCs as much as possible because these damage ozone layer. Okay, so these have been ruled out in a lot of countries. There are still some old refrigeration systems using them, but they will be out of operation in a few years' time, if not already out of operation. So R22 is what's used in window air conditioners. R134A is a very common refrigerant, which you will find. Ammonia is used for industrial systems. And R600 is also being used in some new refrigerants, in some new refrigerators that we see in the market. So have a look at extra electronic stores or some other electronic stores and figure out which of these refrigerants are being used, right? So you'll get a very good feel for what's happening, right? So it's a very good way to relate what we study in the class to what's happening in the world, because the reason you're studying this is to go and solve problems in the real world, right? So you need to know the relation. Okay, so this is all for the different refrigeration types and their characteristics. Now let's talk very briefly about the innovations that have happened in terms of refrigeration systems. Now, till now, we have been talking about the simple vapor compression refrigeration cycle, and we spent some time discussing it because it is the most widely used refrigeration cycle, right? And it's more than enough for a lot of refrigeration applications, right? If we talk about domestic refrigeration applications, it does an excellent job. It's more than enough, and it's really, really nice in the sense that it's simple, it's inexpensive, it's very reliable, and almost maintenance free, right? I'm sure a lot of us have refrigerators which have been working trouble-free for the last 10 plus years, right? So these are excellent devices. But when we talk about some specific applications, especially when we talk about large industrial applications, simplicity is not so much of a concern as much as efficiency is, right? So they really want something which is very efficient. They can handle the maintenance requirements of complex systems. So when they're looking for efficient systems, the simple vapor compression cycle is not enough for them, right? And it needs to be modified. Now, there are a couple of modifications that are done, especially when we are trying to achieve moderate or very low temperatures, right? So the two major modifications that are done to the simple vapor compression cycle are what is called as the Cascade refrigeration system and the multi-stage compression refrigeration system. We'll talk about the Cascade in detail today. We'll talk about multi-stage when you come back on Thursday, inshallah. So this is a schematic for a Cascade refrigeration system. So this is kind of similar to the binary cycle, if you recall, in the sense that there are two different working fluids and two different cycles with a heat exchanger in between, okay? So why do we use Cascade refrigeration systems? Well, we mainly tend to use Cascade refrigeration systems because let's say we are trying to achieve very low temperatures, okay? Let's say TC is minus 30 degrees Celsius or minus 70 degrees Celsius, which is kind of needed when you're handling some specific gases or for some specific industrial applications. So when you're trying to achieve such low temperatures, it is not really efficient to use just one working fluid or a simple refrigeration cycle to achieve or to go to such low temperatures. So what makes sense rather is to basically split it into two, have one high temperature cycle, which is using the appropriate refrigerant, and use another low temperature cycle, and then have them mixed at the condo flow heat exchanger, right, where they exchange heat, which acts as the condenser, for one, where it's rejecting heat, and acts as the evaporator for the other, where it's accepting heat. So this is basically a way to split the two, split the overall heat input requirement and break it down into two, because we need to reject to the atmospheric condition, which is basically 35 or 25 degrees Celsius, depending on the ambient condition. And we are actually trying to transfer heat from a very low temperature or maybe moderately low temperature. Okay, so this breaking it down into two cycles makes more sense because sometimes it's just too large for a single refrigerant to handle it. When I say too large, it's simply basically I'm just trying to say that the compressor work input would simply be too large. So it makes sense to break it down into two. What happens when you break it down into two? Well, the desired output remains the same. The desired output is what is happening here, the heat being absorbed in the low temperature evaporator. The work input is now happening at two different places, in the compressor in cycle A and the compressor in cycle B. So we have the work input coming from two different places. Interestingly, breaking it down does not actually decrease the COP, it actually increases the COP, okay? And it just increases the COP because we are achieving refrigeration in a more efficient manner, in terms of the characteristics of the fluids that are being used, right? So in terms of the pressures, the pressure temperature match, that is. So when we talk about industrial systems, they actually don't use two stages of cascading. They typically tend to use 3 or 4 stages of cascading. So you have two more of these cycles, or at least one more of the cycle, right? So cycle ABC, for example, or cycle ABCD. Okay, so this is something that's also, this is a very simple modification, but it's a very useful modification. Okay, and there will be a homework problem most likely on this. So I mean, we will solve a problem based on the other innovation that we talk about. This one is rather simple, very similar to the binary cycle. So we will not do it in the class. So the second modification is the multi-stage compression refrigeration system. Now, this is kind of similar to the concept of open feed water heater, right? So this is essentially the cascade refrigeration system, but instead of having, two separate stages because you're using two refrigerants, here we are actually just using a single refrigerant. And therefore, to improve the heat transfer that's happening between the two stages, right? Between the upper stage and the lower stage, we just have a flash chamber, or let's say a mixing chamber, right? So, and we have it because it has better heat transfer characteristics than having a counterflow heat exchanger. So we will talk about this in more detail on Thursday. That's it for now, and then see you on Thursday. And make sure you go through this because I'll be asking 3 questions in the pop quiz in the first 10 minutes of the class on Thursday. So that's it for me, and see you on Thursday then.